we're focusing on a couple of things that are kind of left behind that we didn't fully get to in the first 2 days. So we talked about the idea of a neutral atom, where the number of protons and the number of electrons were identical, were equal to each other. What if they're not equal to each other? If they're not equal to each other, then what we're going to have is an imbalance of charge. And we call a species that has an imbalance of charge, we call that an ion. And ions come in two different forms. We either have the ions that have more protons than electrons, so therefore they have a greater positive charge. Those are called cations. And we have negative ions, those that have more electrons and those are called anions. And I made reference to anions when we were talking about the oxoanions just a couple of minutes ago. So we can calculate the charge on any ion by simply taking the number of protons in that atom and subtracting from it the number of electrons. So, for example, neutral neon, neon without a charge. Atomic number of neon is 10. If it's neutral, it would have 10 electrons as well. Charge on it, 10 minus 10 would be 0. That's why it's neutral. But let's say that we did have a charged version of neon. Let's say that we had those 10 protons, because the proton number can't change. Now we only have 8 electrons. Find the charge on that particular species of neon. I would take the 10 protons minus the 8 electrons, and I would get 2, positive 2. And it would be positive 2 because we have more positive charges than negative charges. Now, we will always show the charge of an ion in the upper right-hand corner of the symbol. So in my example, I had 10 protons and 8 electrons for a positive 2 charge. That would give me neon with a positive 2 charge. So I show the positive 2 charge there as a part of that neon symbol. So that's what ions are from a definition standpoint. What does that look like in practice? How do we actually get to it? Well, in practice, we get positive ions or negative ions through the movement of electrons. So we know that the atomic number of an atom can't change without changing the element itself. So neon's always going to have 10 protons in it. Oxygen's always going to have 8 protons in it. If I'm going to have an oxygen with a charge on it, it's going to be because the electrons are coming in and out, not that the protons are coming in and out. Because if I change the proton number, I change the identity of the element. So for positive ions, again, we call those cations. The resulting change is through the loss of electrons. So in the case of lithium, if lithium were to lose an electron, it would take on a positive 1 charge because it lost that 1 electron. But ultimately, lithium could lose more than 1 electron. Whatever charge is associated with that lithium would be directly related to how many electrons it actually lost. So if it loses 2 electrons, it would have a positive 2 charge. If it loses 3 electrons, it'd have a positive 3 charge. In the case of lithium, it can't lose any more than that because it only has 3 electrons to begin with. But ultimately, the charge on that cation would be based on how many electrons it lost. By contrast, anions are all about gaining electrons. So how do I get a negative charge? I have to add electrons along the way. So take fluorine, for example. Fluorine has 9 protons and 9 electrons. If it were to add an additional electron and go from 9 to 10, its charge would be -1. Because again, charge is equal to protons minus electrons. And if I have 9 protons and now 10 electrons, because I added that 1, that gets me to that -1. But again, fluorine has the potential that it could add more than 1 electron. What if it added 2 electrons? Well, then its charge would be -2. What if it added 5 electrons? Well, then its charge would be -5. The number of electrons added is equal to the total charge, just negative. Now, luckily for us, ionic charges are not the wild, wild west. There are usually some patterns that are present to help us out along the way. And so if you have your periodic tables from earlier this week, this would be a great thing to add to those tables because there are some characteristic charges that are associated with some of those families that we talked about. So for example, the alkali metals, group 1A, these will always form +1 charges when they make ions. Now, we don't have to get into the reasons why, but that's a different conversation for another day. But we do know that all of those alkali metals always make +1 charges. Similarly, we know that the alkaline earth metals always make a +2 charge. If we go to group 3A here, generally speaking, those in group 3A are going to make +3 ions. Flip it over to the non-metal side. The halogens, group 7A, 17, always make -1 charges. The oxygen group always make -2 charges. The nitrogen group always make -3. Now, one important note about all of those charges apply only to the non-metals in those groups. So remember, this staggered staircase line here separates the metals and the non-metals. Once you cross over that line, you're not going to find negative charges on those elements. So, for example, got bismuth here at the bottom of 5A. Bismuth doesn't make negative ions. Bismuth makes positive ions. And usually of the +3 variety, although it does have the potential to make others. And so this note here in the middle is kind of important. Transition metals, that is the metals that are not in the main groups, metals that kind of work their way toward the staggered staircase here, they can take on variable charges. So they can have charges anywhere from +1 to +7. And which one they take on kind of depends on which metal you're talking about. So we usually have to use context clues or the names of the compounds themselves to figure out what charge is actually there. And that's something that we'll talk about next week. But in the main group elements, very predictable kinds of charges. The other thing that I wanted to make mention of today is the concept of an isotope. Now, isotopes, we've talked about the idea of the nucleus. Talked about this idea that the nucleus has protons in it and neutrons in it. We haven't really talked about any kind of variability in those nuclei, though. And so the question becomes, we know that the identity of the element is tied to the number of protons in that nucleus. Do the number of neutrons matter? And the answer to that question is, for identity purposes, no. For stability purposes, yes. Different numbers of neutrons do make a difference in terms of how well that particular version of the atom is going to maintain stability, or whether or not it becomes radioactive. So the term isotope refers to, I've got an atom, I've got a series of atoms. They all are of the same element, but their nuclei are not necessarily identical. So I've got a nucleus here with 10 protons in it and 10 neutrons. I've got another nucleus here with 10 protons and 11 neutrons. They're both neon. There's a slight difference in the nucleus of the one versus the other. The term mass number helps us to differentiate between these two different forms, these two different isotopes. Mass number tells us how many particles are in that nucleus. So it is the sum of the number of protons and the number of neutrons. So if you remember from earlier this week, we talked about the atomic number. The atomic number was just the number of protons in the nucleus. The atomic number is given to us by the capital letter Z. Mass number includes that while also adding in the number of neutrons. And so what you can see is that with these two together, I can write a couple of other equations. Mass number is equal to atomic number plus neutrons. Or if I'm just looking at neutrons, neutron number is equal to atomic number subtracted from mass number, A minus Z. And so if we put all of these together, what we have is something called isotope symbol notation. Isotope symbol notation can come into two different forms. This form here is probably the more common form. We see it especially if we are dealing with radioactive isotopes, because we can use that notation to show how that isotope breaks down, how it decays. But the key features of it are we've got the chemical symbol itself, and we also have the mass number and the atomic number stacked on top of each other to give us a very clear picture of what that nucleus looks like. Mass number tells us how many total particles there are in the nucleus. Atomic number tells us how many of those particles are protons. And if I subtract the two, that would tell me how many neutrons are there. This notation can also take on a different form like this, where instead of having all the numbers stacked, we just show the atomic symbol and the mass number, and we put those two connected by a hyphen. So neon 20, neon 21, neon 22, in that kind of way. So I'm going to stop right here, and stopping here is going to have two consequences. First of all, I didn't get a chance to talk about atomic mass. And atomic mass is kind of a complicated calculation. You're welcome to try it out on your own, but chances are pretty good you might get lost along the way. We'll talk about it first thing on Monday, which means this post-lecture assignment will be due on Monday night now instead of this evening. Have a great weekend.